Welcome to today's paper reading. Today's paper is titled SynJax, Structured Probability Distributions for JAX. This paper was published on AR14 by Miloš Stanojević and Laurent Sartran from Google DeepMind. The abstract highlights the role of deep learning libraries in advancing the field by optimizing execution for hardware accelerators, allowing users to focus on modeling. However, this has primarily benefited models like transformers, which map easily to vectorized computation. In contrast, models that account for structured objects, such as trees and segmentations, have not seen the same benefits due to the need for custom algorithms that are challenging to implement in a vectorized form. SynJax addresses this issue by providing an efficient vectorized implementation of inference algorithms for structured distributions, enabling the development of large-scale differentiable models that explicitly model structure in the data. The code for SynJax is available on GitHub. In many domains, data exhibits a latent structure that explains how its parts fit into a larger whole. This structure varies depending on the task and can be observed in natural language and biological data. Incorporating this structure into deep learning models can lead to better generalization, the ability to incorporate problem-specific algorithms, and improved interpretability. While autoregressive models are commonly used, they face challenges in inference tasks. Factor graph models offer an alternative that can efficiently compute inference tasks. The SynJax library addresses the lack of ergonomic libraries for structured distributions, providing easy-to-use structure primitives within the JAX framework. Figure 1 illustrates various natural language structures. It shows a sequence of words forming a sentence, with each word assigned a part of speech tag, creating a linear chain dependency. Additionally, the sentence is segmented into smaller, contiguous groups, represented by bubbles. These structures are fundamental in understanding and processing natural language, showcasing the complexity and hierarchical nature of linguistic data. Figure 2 illustrates an example of implementing policy gradient with self-critical baseline and entropy regularization for spanning trees. The code snippet demonstrates how to compute policy gradient loss, which involves multiple quantities such as sampling, Argmax, entropy, and log probability. The structure in this example is a non-projective directed spanning tree with a single root edge constraint. SynJax automates the computation of these quantities using specialized algorithms, allowing users to focus on modeling aspects without needing to implement specific algorithms or understand their details. In the context of structured distributions, factor graphs are used to represent distributions over most structures. These are bipartite graphs that include random variables and factors connecting them. Each factor is associated with a non-negative scalar potential for each possible assignment of the random variables in its neighborhood. The potential of a structure is the product of its factors. The probability of a structure is found by normalizing its potential, which involves dividing by a normalization factor often referred to as the partition function Z. This process can be conceptualized as a softmax operation over a vast set of structured outputs, sharing substructures. The probability of a structure in a factor graph is defined by equation 2. While computing the numerator is straightforward, the denominator, known as the partition function, is more challenging due to the exponential number of valid structures. For sequence tagging, linear chain CRF models use the forward algorithm with a complexity of O(m) to the power of 2n, where m is the number of tags and n is the sequence length. A parallel version of this algorithm, proposed by Sarka and Garcia Fernandez, has a complexity of O(m) cubed log n, which is efficient for cases where m is much smaller than n. Segmentation with semi-Markov CRF involves an adjusted version of the forward algorithm that accounts for transitions over multiple tokens, running in O(sm)(2n), where s is the maximal size of a segment. In many cases, we are interested in the probability of a particular part of a structure, regardless of the overall structure. This requires computing the marginal probability, which involves summing the probabilities of all structures that contain that part. Traditionally, this was done using specialized algorithms like inside-outside or forward-backward. However, these methods do not apply to all types of distributions, such as non-projective spanning trees. A more general approach is to use the gradient of the factor's potentials with respect to the log partition function. This allows us to use any differentiable implementation of the log partition function and apply backpropagation to compute the marginal probability. This method is versatile and can be applied to structures that do not fit the belief propagation framework. To compute the most probable structure, the belief propagation algorithm is utilized with the max plus semiring instead of the log plus semiring. This approach allows for the computation of the gradient of part potentials with respect to the Viterbi structure potential. For non-monotone alignments, the Jonker-Valgenant algorithm, implemented in SciPy, is employed. In the case of spanning trees, Eisner's algorithm combined with the max plus semiring is used, though Kuhlmann's tabulated arc hybrid algorithm is found to be faster. The reweighting trick is applied to enforce the single-root constraint with Kuhlmann's algorithm. For non-projective spanning trees, a combination of reweighting and Tarjan algorithm is used. Figure 4 presents a speed comparison of different algorithms used for computing the maximum projective spanning tree. The comparison includes CPU and GPU implementations of SynJax using both Eisner's algorithm and Kuhlmann's tabulated arc hybrid algorithm. The graph size does not significantly impact the performance of these vectorized implementations, as most operations are parallelized. This figure highlights the efficiency gains achieved by switching from Eisner's algorithm to Kuhlmann's algorithm, particularly on GPU implementations. In the context of sampling structures, there is no proper sampling semiring due to the requirement for deterministic output in semirings. However, the semiring framework can be adapted to include non-deterministic aspects. Researchers like Aziz, 2015, and Rush, 2020, have employed a semiring that operates like a log semiring during the forward pass but performs sampling during the backward pass, aligning with the forward filtering backward sampling algorithm. For non-projective spanning trees, which do not support the semiring framework, custom algorithms are necessary. These include Colborne's algorithm, which has a fixed runtime of O(n)(3), but is susceptible to numerical issues due to matrix inversion, and Wilson's algorithm, which is more numerically stable but has a runtime dependent on log potential values. Additionally, SynJax supports vectorized sampling without replacement, as described by Stanojević, 2022. The challenge with traditional sampling algorithms is that they provide unbiased samples but are non-differentiable, leading to high variance in gradient estimates. This issue can be addressed using the log derivative trick from the reinforce algorithm, but it still results in high variance. To overcome this, several differentiable sampling algorithms have been proposed that introduce bias but offer low variance gradient estimates. SynJax implements a variety of these methods, including structured attention, relaxed dynamic programming, and perturb-nmap, among others. The cross-entropy H, P, Q is computed using the formula involving the sum of P, T, log Q, T, over all T and T. This computation can be reduced to finding marginal probabilities of one distribution and the log partition of the other, which can be efficiently computed in SynJax. Entropy H, P, is simply the cross-entropy of a distribution with itself, making its computation straightforward. The KL divergence DKL, P, Q, is defined as the difference between the cross-entropy H, P, Q, and the entropy H, P, and it can also be computed efficiently. The JAX typing library significantly enhances the SynJax code by ensuring it is both concise and well documented. It also automates the verification of user-provided arguments, which is crucial given the complex shape constraints of each distribution. To simplify structured algorithms that require complex broadcasting and reshaping operations, the INSIM implementation from the core JAX code was modified to support arbitrary semirings. This modification not only made the code shorter but also easier to read. Additionally, checkpointing techniques are employed to optimize memory usage and speed up computations, particularly on TPUs, by avoiding the memorization of tensors that can be quickly recomputed. Table 1 presents a detailed comparison between SynJax and Torch struct in terms of lines of code, LOC, for log partition computation and the relative speedup in calculating marginal probabilities. SynJax demonstrates significant efficiency improvements across various distributions. For instance, SynJax's implementation of non-projective CRF achieves a remarkable 71 times speed-up compared to torch struct, while maintaining a codebase that is 16% the size of torch structs. This highlights SynJax's concise and high-performance approach to structured probability models, making it a compelling choice for large-scale training on modern hardware accelerators. SynJax offers a unified interface for various distributions and inference algorithms, ensuring reproducible sampling through controlled randomness seeds. It employs a more general approach to entropy computation that is not dependent on semirings, making it applicable to all distributions. In terms of performance, SynJax is implemented in Python and optimized with JAX.jit and number.jit, making it both concise and faster than comparable libraries like torch struct. SynJax also provides the fastest and most feature-rich implementation of spanning tree algorithms, outperforming other libraries in this domain. Figure 3 presents a speed comparison between different libraries handling non-projective spanning trees. The primary focus is on SynJax and the code from Stanojević and Cohen, which has been optimized using number. The figure highlights the significant performance improvements achieved by the number-optimized code, particularly for larger graphs. This comparison underscores the efficiency gains possible through targeted optimization techniques in computational linguistics. SynJax addresses the challenge of implementing deep neural models on modern hardware accelerators, making large-scale training of structured models feasible and easy in JAX. This development is hoped to encourage research into alternatives to autoregressive modeling of structured data. However, SynJax still faces limitations in speed and memory usage, particularly due to the use of large temporary tensors and dynamic programming algorithms. Potential optimizations include custom kernels written in Pallas and leveraging specialized hardware for certain operations. The authors acknowledge contributions from the Google DeepMind language team, Patrick Kidger's work on Equinox and JAX typing, and Sasha Rush's open-source torch struct library. Thank you for watching.